tools that is used for analyzing basically anything you can write down as a matrix. You can pull apart into a special sort of objects called eigenvalues and eigenvectors, and it's going to look really weird when we do it. It has tons of applications all over mathematics. So for those of you that are going to do statics in the future, like serious statics, you can write down force vectors, stress vectors in a matrix, and you pull it apart into eigenvalues and eigenvectors, and it decomposes the tensor into the right bits, right? So there's a practical thing that you do from that. You might be doing it at the moment.
No, do that right now. Teach us.
I cannot do that right now. So the other thing that you can do with this is you can solve systems of differential equations. So so differential equations that interact with each other, like simple predator-prey models, right? So if you do anything where there's multiple things going on that have dependence on each other, so that shows up in biological modeling, it shows up in dynamics, it shows up in fluids, it shows up in interactions between different domains of physics or applications. You use the same methods to do that. So today I'm going to talk about sort of an outline, a motivation for the question we're studying. I'm going to show you what a system of differential equations looks like. I'm going to argue that the problem that we want to solve is a very particular matrix problem. And then I'll show you how it works, but not why. And then we're going to talk about complex numbers, because complex numbers are sort of intrinsic to all of this. So I don't have any notion of how much experience people have in here with complex numbers. So we're going to start with a brief introduction to complex numbers and their arithmetic, and then I'm going to show you Euler's identity. So, to begin with, so this is sort of a motivation for what we're doing, sort of a motivating question. If I write down a very easy differential equation, dy dx is equal to y. But that's pretty easy to solve, right? You can think of a function that's equal to its own derivative. There's only one. Kind of, it's a unique thing.
Zero?
Other than the non-zero function that's e to the x. Right, so yeah, the only non-constant function that's equal to its own derivative, right? So y is equal to e to the x. So e to the x has this weird property that if you took the derivative of e to the x, you get back e to the x. I'm going to change this differential equation and make it slightly more complicated by putting a constant in there. What if I took dy dx and I asked for functions that were equal to some constant c times the original function? So dy dx is equal to cy, a function that is equal to c times its
e to the cx.
E to the cx will do that, right? So this is solved by y is equal to e to the cx. So this has the property that if you took the derivative of e to the cx, you get c times e to the cx. If I translate what we're doing here into the language of matrices, there's a similar matrix question I can ask, which is, okay, this operation, taking a derivative, is linear, which means it acts like matrix multiplication. So I can ask this similar question: are there problems where I start with a matrix A and I act on a vector v, and I get a scalar multiple of that same vector back out the other side? So this is a representative of a large class of questions that look like this. Something acting on the vector v spits out a vector pointing in the same direction but scaled. Okay. So where these matrices are going to come from in a lot of the problems we're working on look like this. Suppose that I give you what's called a simple predator-prey model. So this is a system of differential equations. So let's let x be equal to like a rabbit population, and y is equal to a fox population. If I have two populations I'm studying in isolation, one very easy model for how their populations interact with each other might be the change in the rabbit population, the rate of growth of the rabbit population, is going to be a function of how many rabbits there are. That's the sort of reproduction part of the rabbit population. So you can think of this as reproduction. Plus a term that involves the foxes. You can think of this as a predation term. the more foxes there are, the more rabbits are getting eaten, right? So there's two things that are interacting that tell you what the growth rate of the rabbit population is. So the growth rate of the rabbit population depends on the number of rabbits and the number of foxes. And likewise, the growth rate of the fox population is equal to the amount of resources they have available to consume. So you can think of this as consumption plus their own reproduction term. So this is an example of a very simple model of what's called predator-prey. These populations are interacting with each other, and so their growth rates depend on more than just how many of them they happen to be, right? There's this interaction between the two equations. And so together, this family of equations is called a system of differential equations. They're stuck together. So the reason that we didn't talk about this earlier in the class is because it's much easier to write down a system of differential equations like this with matrices. So if I translate this, I mean, that just to me looks like x prime is equal to a11x plus a12y, and y prime is equal to a21x plus a22y. If you get around linear algebra long enough, you look at the right-hand side and say, that looks an awful lot like a matrix times a vector. You can rearrange this into the equation x prime y prime is equal to a11, a12, a21, a22 times xy. And if I want to use vector notation, I could rewrite this as x prime is equal to a times x. So this vector setup here, this vector setup is a way of recording a system of differential equations. And just like when we wrote down d by dx of y is equal to cy, the solutions were determined by that constant value c. That matrix A is going to tell us what these solutions look like. So this matrix will tell us what the solutions to this sort of equation look like. I won't tell you what they are yet because this is the subject of chapter 8. I will say that the problem this translates into, it turns out we can solve this problem for the functions x and y that make this true if we can solve this question. If I can figure out vectors and scalars that make this equation true, if I give you a matrix A and you can find vectors and scalars that make this equation true, if you can solve this equation, you can find the solutions to this one. So this equation is really important. It is called the eigenvector problem. Write that down. Okay, so given a matrix A, this has got to be a square matrix, the eigenvector problem, I don't know if it's obvious to you, but this was invented by Germans. The eigenvector problem asks, to find vectors v and scalars c so that AV is equal to CV.
Well, vectors named vector M or same vector vectors. Are they unrelated?
I don't know. Okay, so I should probably convince you that these things exist before we start. Now, the reason that we're sort of working in parallel with differential equations is because with this language, we might say e to the cx is an eigenvector for the problem d by dx of y is equal to cy. I feed in the vector and I get the same thing out again but multiplied by some scalar. In the matrix case, I could write down this matrix. So I'll give you an example of what one of these looks like. So let's look at the matrix -2, 5, 6, -1. So that's our matrix A. And I'm going to give you a vector v1, which is equal to -1, 1, and a vector v2, which is equal to 5, 6. And what we want to do is we want to show that v1 and v2 are eigenvectors, which is to say we want to show that they satisfy that equation AV is equal to CV, and then we want to find what are called the eigenvalues. These are the C numbers that show up in that equation. So essentially, we want to show that if we take V1 and multiply it by A, we get a scalar multiple of V1 back out again. That is to say, I want to show that A eats V1 and then takes that vector and keeps it pointing in the same direction, just possibly scaling it. So just to reiterate, before we do this, if AV is equal to CV, VC is called an eigenvalue, and V is called an eigenvector. I guess I say associated eigenvector. Yep.
Are those the same vectors? Or separate vectors?
You mean here?
Yeah. Yeah.
This is the same vector on both sides.
Okay.
The way to think about this is A is a machine that eats a vector and spits out another vector, right? The vector that if the vector it spits out points in the same direction as it did when it went in, then it's an eigenvector. So what I want to demonstrate is these exist. So if you take the matrix -2, 5, 6, -1, and you multiply it by -1, 1. Then what you get out is 2 plus 5 and -6, -1 plus 1, say -6, yeah, -1, which is the vector 7 -7. Now that is not the original vector. It's not the original vector. But it is -7 times the original vector. Right? So it's not the original vector, but it's a scaling of the original vector. So here what we're thinking is, this is the matrix A, this is the vector V, this is the same vector V over here, and this was its scaling factor C. So V, because we've satisfied the equation A times V equals C times V, V is an eigenvector, and C is its eigenvalue. So the conclusion here is -1, 1 is an eigenvector with eigenvalue -7. Geometrically what's going on is A takes that vector, flips it backwards, and multiplies it by 7. So we can do the same thing. Oh, okay, do you like vocabulary? Together, these are called an eigenpair.
You know eigen just means own?
Uh-huh.
It's its own vector?
Yeah.
That's crazy.
That's because it's mapping it to itself, yeah.
So it's only complicated because it's not
I mean, yeah, it's like...
only a weird word.
It is. I didn't invent it. -2, 5, 6, -1
Yeah.
times 5, 6 is -10 plus 30, which is 20, and then 30 minus 6, which is 24. And again, that is not the original vector, but it is 4 times the original vector. So A times V is equal to C times V. So 5, 6 is an eigenvector. And 4 is its eigenvalue. And together they are an eigenpair. And a lot of professors will call all this eigenstuff. So, you know. Okay, so now, basically the problem is, what I've shown you now is an example of, I gave you a matrix and I give you a couple of vectors and I said, look, there's a magic equation. Do these satisfy it? And you can calculate it and say, yes, they satisfy the equation. I didn't tell you how to find those vectors. Okay. So when we start working on actually chapter 7.1 proper, I will show you exactly why what I'm about to do works. I'm going to show you the procedure that you would use, just the part of the procedure that you would use to find the eigenvalues. Because there's an argument that I want to make about learning complex numbers and why we want to do it here. Okay, so I've shown you nothing about where these come from. I just showed you this matrix has these vectors and they both satisfy the eigenvector equation. So I'm going to show you where the eigenvalues at least come from computationally as a black box for now, and then next time I'll show you why it works. So for now we're just going to write down C1 was equal to 4 and C2 was equal to, sorry, this was minus 7 because that was the one that went with this vector, and C2 was equal to 4. So I'm going to show you like how all of the methods that we've done so far come together to tell us what those values had to have been. So this is sort of, like I said, introduction to all this crap because people find this really confusing. So this is what the method looks like. In order to find C1 and C2, I'm going to solve this weird looking equation. I'm going to write down the determinant of the matrix A, and I'm going to subtract off lambda times the identity. So lambda here is the variable. This is traditional. You can think of this as a variable. So I take the matrix A, I subtract off an identity matrix that has a variable multiplied by it, and then I take all of that and I set it equal to 0, and I solve for lambda. And I promise next time I will tell you why this works. So, but the point today is we're going to look at polynomials. So for this particular problem, the matrix A is equal to minus 2, 5, 6, minus 1. And if I subtract off lambda times the identity matrix, so this is A minus lambda I, then we get the matrix minus 2 minus lambda, 5, 6, minus 1 minus lambda. I just scalar multiply the lambda inside the identity, so minus 2, 5, 6, negative 1, minus lambda, 0, 0, lambda. And the way that you add or subtract matrices is you just add and subtract the entries. Now what the algorithm says to do, this black box I'm asking you to accept for right now, is that I should now take the determinant of that matrix. So the determinant of minus 2 minus lambda, 5, 6, minus 1 minus lambda is minus 2 minus lambda, minus 1 minus lambda, minus 30. The 2 by 2 determinant is this times this minus this times that. So A times D minus B times C. Double check I got my signs correct here. So this is equal to, okay, so we got a, I guess, I have a friend of mine at the department that doesn't like to say FOIL, so he says FLOY. So we're going to FLOY the polynomial. And that's going to get us 2 plus lambda plus 2 lambda plus lambda squared minus 30 is equal to 0, because the black box that I told you right now says take the determinant and set it equal to 0. That's going to tell us that lambda squared plus 3 lambda minus 28 is equal to 0. Write this up here. So right now we've got that the determinant of a minus lambda I is equal to 0 has turned into the equation lambda squared plus 3 lambda minus 28 is equal to 0. And that tells us lambda plus 7 times lambda minus 4 is equal to 0. So lambda is negative 7 or lambda is 4, which are the exact two numbers that we found up here. Right? So this black box, whatever it's doing, has produced the right values. If you want to know like what's actually happening here, we're figuring out places where that matrix doesn't have an inverse. So I'll show you why next time, but that's what's actually happening. So it's easy to imagine that when we're structurally decomposing a matrix, this is going to allow us to take a matrix and blow it apart into its important pieces. The eigenvectors turn out to be really important for understanding the information that a matrix contains. So what if I wrote a matrix down, and instead of getting a polynomial that looks like this, you run the same process, right? I give you a matrix, you run the process where you've calculated the determinant, you've written down this polynomial, and at the last step, you don't get something that you can factor using methods you learned in 8th grade. Instead, you get something that looks like this. So what if you had to solve lambda squared plus 2 lambda plus 5 is equal to 0. And then you go in there and you say like, well, I learned, so you write down the quadratic equation, because you really like the quadratic equation for some reason, even though completing the square is the right way to do all these things. But you like complete the quadratic formula so much that you write it down, and you notice that inside the square root is negative, and so you conclude that it's an irreducible quadratic. And that is not acceptable for us. There's no such thing as irreducible quadratics. They don't exist. So we're not going to allow ourselves to get away with that. Now, I could solve this using the quadratic formula if I was willing to use imaginary numbers. But I'm not going to do that. I'm going to complete the square instead. And so I'm going to remind you what's going to happen, and I'm going to walk you through complex numbers. If I solve this with completing the square, because I'm not insane, I would write lambda squared plus 2 lambda is equal to negative 5. And then I would add 1 to both sides to get lambda squared plus 2 lambda plus 1 is negative 4. And then I would factor this side to get lambda plus 1 squared is equal to minus 4. And then I square root both sides. Lambda plus 1 is equal to plus or minus the square root of negative 4. And so lambda is equal to minus 1 plus or minus the square root of minus 4. It sure would be great if the square root of minus 4 made sense, so I could factor this equation down into its lowest form, so I could figure out what its roots were. I don't want there to be irreducible quadratics. I want to know what the zeros of the function are. So we just declare this to be equal to 2i, where I is the imaginary unit. So what we're going to talk about for the rest of the class is everything we're going to be doing for the next couple of weeks is going to involve factoring quadratics, and often the answers will be complex numbers. So I'm going to walk you through complex numbers. Like a sort of refresh you if you've never seen them before, or like show you if you've never seen them before, refresh you if you haven't. Almost everybody in here is going to see something new in the course of this conversation. Before I get started, I'm very curious. How many of you would say confidently that you have a thorough understanding of the arithmetic and simple algebra of complex numbers? Okay, it's like 6 or 7 of you. Okay, so we're going to start a quick walkthrough of what how complex numbers are defined. A version of what they represent you may not have seen before, because the fact that these are called imaginary is kind of not doing them any favors. In fact, one of the guys, the really famous mathematician Gauss, if you know who Gauss is, when he learned that somebody was calling these imaginary, he basically wrote letters disparaging the name. Like, why would you call those imaginary? It's like you're making the people hate them before they even start. So I'm going to try to show you an interpretation of imaginary numbers, complex numbers, that makes them feel like objects that might actually come up in your everyday life. They're very important for the study of science. So, unfortunately, in some ways, they're more important than the real numbers. The rest of your life is going to be nothing but sines and cosines and complex numbers. Welcome to engineering in the modern age.
Yes.
Yeah. So, the imaginary unit. So this is now that we've sort of gotten the problem down to, we want to study these, we can't solve these unless we know how to work with imaginary numbers. So the imaginary unit, I, has the property that I squared is equal to minus 1. You can imagine at the beginning it's a formal symbol that will turn out to have all this meaning later. So, if I squared is equal to minus 1, it means successive powers of I follow a pattern. If I squared is negative 1, then I to the third is I squared times I, which is minus I. I to the fourth is I squared times I squared, which is minus 1 times minus 1, which is 1. I to the fifth, you might think that you never have to deal with I to the fifth, but you do. You've got to know I for all of them. So, what's up, Arlo? Oh, okay. Is I to the fourth times I, which is 1 times I, which is I. And then the pattern continues. I to the sixth is equal to minus 1, and I to the seventh is minus I, and I to the eighth is 1, and so on, right? So it's this period 4 pattern that repeats. That's a 7, right? Okay. So we can assemble, just like when we wrote down the solution to that differential equation, our solutions look like lambda was equal to minus 1 plus or minus 2i. These are examples of objects called complex numbers. A complex number has the form z is the traditional letter for representing complex numbers. Z is equal to a plus ib, where a and b are real numbers. Okay. So a is called the real part of z. And b is called the imaginary part. Of z. So already, right now at the very beginning, I want to give you an interpretation of complex numbers that will hopefully justify why we want to use them. So, if a complex number has a real part and an imaginary part, and it's going to turn out that the way that we add them is we add the real part to the real part and the imaginary part to the imaginary part, like terms, then we can think of complex numbers as basically sitting in a two-dimensional plane where the real part lives on the x-axis and the imaginary part lives on the y-axis. So if I wrote down the number 2 plus 3i and I wanted to plot that on a two-dimensional graph, I would go 2 units in the real axis and 3 units on the imaginary axis, and the number would be right here, the number 2, 3. So there's a connection between complex numbers and numbers that are points x, y, in R2. This is the most natural way to think about complex numbers. And you might say, well, R2 is good enough. Why don't we just use R2? And the answer is, R2 has 2 different pieces. It has a vector. It's an x and a y component. Complex numbers are single things. They're just numbers. They follow the rules of numbers. So it's like I'm storing 2 dimensions worth of information in a single number. That's the whole point of why people use these things. It starts there. Okay. So if I claim these are numbers, they should follow some arithmetic rules. So our first operation is called the complex conjugate. Conjugate is a term you may have heard in the past. If you've ever cleared a square root from the bottom of a fraction, you've multiplied top and bottom by the conjugate. So the complex conjugate is denoted by z bar. A plus IB with a bar on top of it. And what that means is just negate the sign of the imaginary part. If you like, up here what it means is if this was 2 plus 3i, then the complex conjugate would be down here at 2 minus 3i.
So you always have.
It's like reflection across the x-axis. What's that?
Why?
It'll make more sense when I get to talking about rotate. So these are ultimately going to represent rotations, and so these are going to be clockwise and counterclockwise rotations is what this is going to correspond to. Okay. For now, you can think of it as an algebraic trick that we're going to need for dealing with division. So how do you add these things? You just compare like terms. So if I write down 2 plus 3i, and I add it to another complex number like 1 plus 6i, then I add, if this was like had a variable in it, you would just combine like terms, and you do the same thing here. 2 plus 1 is 3, 3i plus 6i is 9i. So real to real, imaginary to imaginary. Multiplying is floying, and then applying I squared is equal to minus 1. So if you're going to multiply, you FOIL, and then you use the fact that I squared is minus 1. So if I did the same two numbers but I multiplied them, 2 plus 3i times 1 plus 6i. So right here we've got a massive advantage over vectors. I cannot multiply vectors. I can multiply complex numbers. 2 times 1 is 2, 3i times 1 is 3i, 2 times 6i is 12i, and 3i times 6i is 18i squared. That does not have the form of a complex number because it doesn't look like a plus ib. So first I'm going to apply the rule that I squared is minus 1. And I'm going to combine like terms. 2 minus 18 is minus 16. 3i plus 12i is 15i. If you've learned complex numbers before, you're dreading the next part because I'm going to show you how to divide them. Everyone hates dividing complex numbers. So how do you divide?
Does it do the multiply inverse?
Yeah, well, the conjugate, but yeah. So you're going to use the conjugate. So what I mean by that is, if I started with 2 plus 3i divided by 1 plus 6i, and I want to put this in a form of a complex number, a plus ib, the trick is I'm going to multiply the top and bottom of this fraction by the conjugate of the denominator. I can't split this up into a real and imaginary part right now because there's an I down here, right? So I have to get the I out of the denominator. How am I going to do that? I'm going to multiply top and bottom by 1 minus 6i. And then I'm going to take advantage of the fact that the difference of squares formula exists. In the numerator, I just get the same multiplication step I did over here. So this is going to be equal to 2 times 1 is 2, 3i times 1 is 3i, minus 6i times 2 is minus 12i, minus 6i times 3i is minus 18i. Squared. But in the denominator, I'm going to get 1 plus 6i minus 6i minus 36i squared. See, what happens is multiplying by the conjugate kills the i's. They're just gone. Because 36i squared is just 36. Or negative 36i squared is just 36. So this reduces to 2 plus 3i minus 12i. I switch the sign because of the I squared to make this an 18. In the denominator I have 1. These cancel and I get a plus 36. So what do I get? 20 over 37 minus 12 over 37i. Negative 9. Negative 9. Sorry, I shouldn't have cut this box off like that. I just mean this. So 2 plus 18 is 20. Negative 12 plus 3 is negative 9. Now there's just a real number on bottom. It's just 37, so I can split the fraction up into the first piece and the second piece. And now it's of the form a plus ib. Okay. So this is your sort of basic arithmetic of complex numbers. Complex numbers have 2 dimensions of information inside of them, but you can treat them like numbers with the full set of arithmetic operations that the regular numbers have. So in that sense, they are superior to vectors because I can just do math with them. So to give you guys the interpretation that I want you to have of what a complex number actually represents and why they show up all over everything you're going to be doing, I need to show you Euler's identity. This is not Euler, it's Euler. So Euler's formula. How many of you guys have seen cis theta before in a class?
My teacher went over the entire, like, walked through the entire.
Yeah, the cis theta, that's the wrong way to do it, right, is the thing. So you go learn cis theta, and I've got to have you replace it in your heads with complex exponentials instead. How many of you guys have seen e to the I theta before? Okay, so some of you. More of you have seen that than the cis. Okay, so Euler's formula says this. This is going to seem weird, because I haven't defined this yet. It says, if I write down a number of the form e, like the exponential, the constant from calculus, to the ix, so I just take e to the x and I put an I inside there. This is the same as the cosine of x plus I times the sine of x. So this is a one number wrap up of these 2 functions. So for any real x, for any real number x, e to the ix is equal to cosine of x plus I times the sine of x. So as a specific example here, if you wrote down e to the I pi over 4, and you wanted to calculate what number that was, that would be the cosine of pi over 4 plus I times the sine of pi over 4, which would be the square root of 2 over 2 plus I times the square root of 2 over 2. And you might ask, well, why would you want to do that? And the answer is, if you put this together with the picture that I can think of this as a vector with an x-coordinate and a y-coordinate, every one of these is on the unit circle. Every e to the ix is a point on the unit circle. So this allows us to encode the unit circle without having to use cosines and sines. Without having to use vectors or an equation, I just get something that produces the unit circle. So what I want you to have in your mind here, when we're doing complex numbers, they're not some mysterious thing that mathematicians invented because we were bored. And they didn't stick in science for the last 300 years because people just had nothing better to do than throw eyes around. The idea is every point on the unit circle has coordinates cosine of x, sine of x. Where x is this angle right here. But if Euler's identity says that cosine of x and sine x as an x and a y coordinate can be written as e to the ix, I could think of this point on the unit circle not as a vector in 2 components, but a single number, e to the ix. Complex numbers represent rotations. Yep.
Why does that work even though there's an I in front of it?
Because we're basically using a transformation to think about this as the vector cosine of x, sine of x. These don't interact with each other. Because of the rules of addition, we only combine like terms. These act like vectors. They have 2 orthogonal directions they point. There's the real part, which only combines with other real parts, like the x-coordinates of a vector, and an imaginary part, which only sees other imaginary parts, like the y-components of a vector. So we're identifying this number with a number in R2, with a point in R2. And so what happens? Okay, so as x goes around, if I say, hey, let x start growing, what happens to that point? Goes around the circle, right? So if I take that point and I let x go around the circle, or x goes goes forward in time, that spins around the circle. What if I make x? What if I looked at the function like, I don't know, e to the I 2x? What would happen is, so say I start, the same function. I start a point here and I say, that's tracking e to the I 2x instead. They all represent angles of the unit circle. What is its behavior?
Just faster.
It goes around the circle twice as fast, right? So these are used in modern engineering and science and applied math to study rotations, oscillations, and vibrations because they encode rotations around the circle. They encode harmonic oscillations of sines and cosine functions. So any field that studies harmonic oscillators or vibration or rotation has to go through this. This is the core of, like, the idea of complex exponentials is the core of sort of contemporary approaches to engineering problems. So they're unavoidable. You'd be living with them. Yep.
Can you graph that as a linear function?
A linear function.
Like on x and y? Or
So basically there's just a translation that goes back and forth between, there's a translation where this is actually really a vector function. So you think about ei2x, you can think about it as the cosine of 2x plus I times the sine of 2x. Or you can think about it as the vector equation from our earlier classes. You could think about this as cosine of 2x, sine of 2x, like a parametric equation. These are all going to represent the same motion. Yep.
Like, what's the reason that the e's and the sines and cosines should?
I'm going to show you right now. Because I wrote this down. I didn't say anything about why it's true, right? Like, what possible connection could these things have?
Series.
All right, indeed. So now, I'm going to look around for who looked the shiftiest on this one. So why? This is the last thing we'll talk about today. Somebody tell me what the series is for e to the x. Just the term-by-term series.
X to the
Hey,
over-
no, hold on. I got to find somebody shifty. No? Okay. Barrett, can you tell me what the series is for e to the x?
1 plus x
Okay.
plus x squared over 2 factorial.
Good, awesome. X to the third over 3 factorial and so on. All right. Remember, I only told you guys back in that class you had to know 4 series, but you had to know them for the rest of your life. All right. Somebody tell me cosine. This is e to the x is equal to this. What's the cosine of x? I can tell you, wiggling enthusiastically is not the same as being shifty. Taylor.
1 minus x squared over 2.
1 minus x squared over 2 factorial plus
X to the 4th.
x to the 4th over 4. Okay, Azalea, I will let you answer the next one. What is the sign?
x minus x cubed divided by 3 factorial.
Good.
Plus x to the 5th divided by 5 factorial.
Okay, so the observation here is, you may have noticed this when we did this, it sure looks an awful lot like the terms of that series are the same as the terms of these guys, right? If you look at the 1 here, it's here, and the x squared over 2 factorial is here, and the x to the 4th over 4 factorial would be the next term up here, x to the 4th over 4 factorial. And you look at the terms of this series, you see an x, and there's an x here, and an x to the 3rd over 3 factorial, and it's right there, and an x to the 5th over 5 factorial will be the next term. It looks like you could just add those together and e to the x would come out. The problem is the sign pattern is wrong, right? This goes, if you try to add them, you get 1 plus x minus x squared over 2 factorial minus x to the 3rd over 3 factorial, and it screws this up. This has all pluses. If you subtract them, the same problem happens. The sign pattern is wrong. So it's almost the case that cosine of x plus sine of x is equal to e to the x. Almost. So the way you fix it is you just chuck I into the series for e to the x. So what if you just threw an I in there? What happens? Well, remember when we did this, I told you that composing Taylor series was really important, right? You could just write down a Taylor series. This one converges everywhere. I could put anything I want into it. Turns out complex numbers are okay too. So I just chuck in an I. And if I write that down, I get 1 plus ix plus ix squared over 2 factorial plus ix to the 3rd over 3 factorial and so on. I'm going to simplify this slightly. Ix plus I squared x squared over 2 factorial plus I to the 3rd x to the 3rd over 3 factorial plus I to the 4th x to the 4th over 4 factorial. And maybe I'll throw in the I to the 5th x to the 5th over 5 factorial. And the pattern continues, right? I've chucked in the I. What does I squared equal to?
-1.
-1. Okay, now I'm going to be very careful. I'm going to write down that this is 1 plus an ix Now I squared is -1, so we're going to get a minus x squared over 2 factorial. I to the third was
Negative I.
negative I minus I times x to the third over 3 factorial. I to the fourth was 1, so we get x to the fourth over 4 factorial. I to the fifth is I, so we get an I times x to the fifth over 5 factorial. And you can see the red terms are the cosine. 1 minus x squared over 2 plus x to the fourth over 4 minus x to the sixth over 6. All of the red stuff is cosine. 1 plus minus x squared. I fixed the sign pattern by putting the I in. Plus x to the fourth over 4 factorial and so on. And all of the green stuff has a common factor of I. So just factor it out. Plus I times x minus x to the third over 3 factorial plus x to the fifth over 5 factorial and so on. And this is cosine of x. And this is I times the sine of x. So it's literally because the power series converge for all these things converge everywhere. Right? So the core idea of complex numbers is that we are somehow wrapping the idea of rotation into a number form. And that's why they're useful. So going forward, like the differential equations that we're going to solve will involve oscillation, and we should expect that we're going to get complex numbers when the answers oscillate. So spring problems, for example. All right, so next time we will go through the formal setup for the eigenvalue problem. Yeah, I'll see you tomorrow.